So I'm going to review topics that are going to be covered on the SLO that you guys are taking. You are allowed to use the review on your SLO as well as Desmos and a calculator. Whether that's your own calculator or that Desmos scientific calculator on Classroom is up to you. So the first thing I want to go over is inequalities. So the first example we're going to do is write an inequality that represents our situation. So suppose baseball games last a maximum of 9 innings and ties are allowed. There is a run rule that states if at least 5 innings have passed and one team is ahead by at least 10 points, then the game is over. If n is the number of innings and d is the difference in points, write the compound inequality that describes the run rule. So first, I'm going to write an inequality that has to deal with n, our number of innings. So I want to pick out the information that has to deal with innings. So we have that there's a maximum of 9 innings and at least 5 innings have passed. So what that tells me is that n has to be greater than 5 and less than or equal to 9. Okay. My second inequality is going to have to do with d, our difference in points. So if I look, a team has to be ahead by at least 10 points. So that tells me that the difference in points has to be greater than or equal to 10. So this is my compound inequality that describes the run rule. Next, I'm going to take my inequality and write the interval notation that represents the inequality. But before I write the interval notation, it's going to be useful to have the inequality version first. So if I'm looking at my first one, I have a closed circle at 1 and an arrow pointing to the left. So the direction of the arrow determines which inequality we're going to use. So the arrow points to the left, which means I have to have a less than, and the closed circle means I have to have an equal to. So x is going to be less than or equal to, and then our value, in which case 1. So closed circle is less than or equal to or greater than or equal to, which would mean open circle is less than or greater than. Okay. When it comes to the interval notation, so this is where I involve the infinities with parentheses and brackets. So every number less than or equal to 1, so less than or equal to always means I start with a negative infinity. And on the right side is where I'm going to put my number 1. And because there's an equal to, that means 1 is included, which means we have to have a bracket. So if I'm going back up here where I'm keeping track of what inequalities use, greater than or equal to or less than or equal to means brackets, and a less than or greater than is going to mean parentheses. On our second one, we have an open circle at 4 and our arrow is pointing to the right. So this is telling me x is going to be greater than 4. So when we have a greater than, we start with our number and we end with infinity. So I want to start with 4 and it's going to get a parenthesis since we have a strictly greater than. Then I'm going to go to infinity, which always gets a parenthesis. So negative infinity and infinity are always going to get parentheses. Lastly, we have a closed circle at 0 and an open circle at 3 with the line in between. So this tells me my value is between two values. So it tells me I have to be greater than or equal to 0, but less than 3. This is an example of an and inequality. So I'm going to have in my interval notation, my numbers are what's inside, so 0 and 3. Because I have an equal to with 0, it's going to get a bracket, and because I have a strictly less than with 3, it's going to get a parenthesis. So the last thing we're going to do is solve the compound inequalities. So anytime you have an and inequality written as a single inequality, your goal is to get x by itself. So anything you do in the middle to get x by itself, you also have to do to both ends. So I have that 2x minus 3. So the first thing I want to do is add 3 on both sides. So negative 9 plus 3 is going to give us negative 6. less than 2x, less than 24. And then I'm going to divide by 2. So negative 6 divided by 2 is negative 3, less than x, less than, and then 24 divided by 2 is going to be 12. So if I now want to write my solution in interval notation, I'm going to have negative 3 comma 12 in my parentheses, and because they're both strictly less than and greater than, both get parentheses. We're going to do something similar on our next example. So I have that 3x plus 1 in the middle, and my first step is going to be to subtract 1 from all the sides. So negative 11 minus 1 is negative 12, less than 3x, less than or equal to 15. Then we're going to divide every number by 3. And negative 12 divided by 3 is negative 4, less than x, less than or equal to 5. So again, my numbers are going to be inside my interval. I have a strictly greater than with a negative 4, so it gets a parenthesis, and a less than or equal to with the 5, which means it gets a bracket. So with compound inequalities, we can have mixed brackets, we can have the same brackets. It really just depends on how it's written. So next we're going to take a look at logarithms and exponential equations. So it's important to know exponential and logarithmic form. So the generalized form for log form is log base b of a equals x. My exponential form is b to the x equals a. I would definitely have these written down so you have them to look back on for the SLO. So my first example, I want to convert log 7 equals x to exponential form. So we have to have a base number to write it in exponential form, which we are not given here. So anytime there's no base written, it's 10. So it's called the common base. So that means my base is going to be 10. I'm going to raise it to my exponent, which is x, equals the number that's inside the parentheses, which is 7. And that's my exponential form. So we're going to do something similar in our next one. We have log base 5 of 8 equals x. So this time I know my base number, my exponential form, is going to be 5. My exponent is going to be x, and then we're going to be equal to 8. When it comes to solving a logarithmic equation, we convert it from logarithmic form to exponential form, just like we did in our previous examples. So I have log base 3 of x equals negative 4. So my base number is going to be 3. My exponent is going to be negative 4, and then I'm going to equal x. So that means x equals 3 to the negative 4th. So now I evaluate 3 to the negative 4th in my calculator, and we're going to get that x equals 1 over 81. So remember, negative exponents don't mean negative answers. They mean fractional answers. So 3 to the negative 4th is the same thing as 1 over 3 to the 4th. And 3 to the 4th is 81. Our second example, we have log base 2 of x equals 7. So my base number for my exponential form is going to be 2. My exponent is going to be 7. And we're going to equal x. So we do 2 to the 7th. And we're going to get that x equals 128. Next, we want to be able to identify a function as exponential growth or decay. So we have our function f of x equals 2 times 4 to the x minus 1. So if you're trying to determine growth or decay, you go based off the general equation, so y equals a times b to the x, and we mostly care about b. So if b is between 0 and 1, we have decay, and if b is greater than 1, we have growth. So the number in front of the parentheses and any number being added or subtracted has nothing to do with growth or decay. We only care about the base number. So in our first example, our base number is 4, and 4 is greater than 1, which means we're gonna have growth. On our second one, we have the equation f of x equals 1/3 to the x. So this time our base number is 1/3, and 1/3 is between 0 and 1. It's a fraction, which means our equation represents decay. So the last thing we want to talk about is solving an exponential equation. So in order to solve an exponential equation, both of your base numbers have to be the same. So base numbers must be the same. So in our first example, we have 4 to the 5th equals 4 to the 3x minus 7. Both of my base numbers are 4, so they are the same, which means if I want to solve the equation, I set the exponents equal. 5 equals 3x minus 7. So now I have an equation where I'm solving for x. So the first thing I'm going to do is add 7 to both sides. We're going to get 12 equals 3x. Then we're going to divide both sides by 3, and we get x equals 4. On our next example, we have 64 equals 2 to the x minus 1. So in this case, our base numbers are not the same. So we want to try to rewrite 64 as 2 raised to a power. And if we do 2 to the 6th, we're going to equal 64. So we have 2 to the 6th equals 2 to the x minus 1. And now that the base numbers are the same, we can set them equal. So we have 6 equals x minus 1. So to solve for x, we're going to add 1 to both sides, and we get x equals 6. Next, we're going to talk about some systems of inequalities and regular inequalities. So the first thing we want to do is graph a system of inequalities. And we can use Desmos to help us create our system. So first we start with y less than 3x minus 4. So I always start by graphing my y-intercept, which in this case is at -4. Then I'm going to apply the slope, which is +3 over 1. Next, we have to figure out what type of line we're going to have, dashed or solid. So if we have a greater than or less than, we're going to have a dashed line. And if we have a greater than or equal to or less than or equal to, we're going to have a solid line. So in this case, we have y less than 3x minus 4, which means we're going to have a dashed line. Okay. Our next inequality is y greater than or equal to x plus 1. So if I start off with my y-intercept, it's going to be at +1. Then I apply the slope +1 over 1. And this time, because we have the equal to, we're going to have a solid line. So that's my first step, is to graph the inequalities. The next step is to shade the overlap region. So the solution region is where the inequalities overlap. And in this case, if we're looking at Desmos specifically, the region where the inequalities are going to overlap is this top region. That's the darkest region if we're looking at the graph on Desmos. So it's important if you're using Desmos to help determine your solution region, you make sure both lines are different colors. Red and blue are always a good choice to use because their overlap region is going to be purple. It's going to be different than the inequalities, and it's going to be easy to detect. Next, we want to solve a system of equations. So we can solve using substitution or elimination, and in this case, I'm going to use elimination because I have one variable that has opposite signs, and it's easy to multiply one of the equations so they have the same coefficient. In this case, I'm going to multiply the second equation by 3. That way, when we add the equations together, the x's cancel. So my first equation isn't going to change. 3x plus 5y equals 12. My second equation, once I multiply every term by 3, is going to be negative 3x minus 6y equals negative 6. Now we add the equations together. The x's cancel. 5y plus negative 6y is going to give us negative y. 12 plus a negative 6 is going to be 6. Then we divide both sides by negative 1, and we get y equals negative 6. Now that we know what y is, we can plug it into one of our original equations to solve for x. And I like to avoid equations that have negatives because it's easy to make mistakes. So I'm going to plug it into the first equation. So we have 3x plus 5 times negative 6 equals 12. 5 times negative 6 is negative 30, so we end up with 3x minus 30 equals 12. Going to add 30 to both sides, so we get 3x equals 42. And then our last step is to divide both sides by 3, and we're going to get x equals 14. So we have two options at this point. I can leave my answer as x equals 14, y equals negative 6, or I can write my solution as a point, which gets written x comma y, which is 14 comma negative 6. The next example is given a graph of an inequality and being able to identify the inequality that would represent. So in our first example, so going back to the system of equations we solved first, we have to figure out, based on the type of line, if it's a greater than or a less than. We have to identify the y-intercept, and we have to identify the slope. So my first example has a dashed line, which means it's going to be a greater than or a less than situation. My y-intercept is negative 2, and then I want to find the slope. So I want to make sure I use two whole number points, like the y-intercept, in this case the x-intercept, and I have to go up 2 and right 5, which means we have a slope of 2/5. So when I write the inequality, we're going to have y. Now I have to determine whether it's a greater than or less than. And because we have shaded below the inequality, it's going to be less than. Then we're going to write the equation of the line, which in this case is 2/5 x minus 2. And we can always use Desmos to help double check that our inequality is correct by graphing it and then making sure our picture on Desmos matches what we have written down and the picture we're given. On our second example, we have a solid line, which means it's a greater than or equal to or less than or equal to. So start off with my y-intercept, which is 3. Now I can't use, when I find my slope, I can't use my x-intercept as the second point because it's not a whole number. But the point 4, negative 2 is a whole number, so I can use that as my second point. So we have to go down 5, and we have to go right 4. So that means our slope is negative 5/4. So now when I write my inequality, we're going to have y, and then determining which inequality, we've shaded above the line, which means it's greater than or equal to. Then we write the equation, negative 5/4 x plus 3. And again, I can double check this using Desmos by graphing our inequality and making sure what we get in Desmos matches the picture we are given. So next we're going to talk about quadratics. So the first thing we're going to do is, given a quadratic with roots -3 and 1/2, we're going to figure out what the equation is in standard form. So when we have roots, we know that when it's in factored form and we solve for x, we get those solutions. So in order to have a root of -3, in parentheses, I have to have x plus 3. Because when I set x plus 3 equal to 0, I get -3. And in order to have a root of 1/2, I know that in the parentheses, I have to have 2x minus 1, because I would add 1 to both sides and then divide by 2. And you can always double check that this is the correct factored form by graphing it in Desmos and making sure that the roots, which are also known as the x-intercepts, match what we're given. So now I want to work on converting it to standard form by distributing. So x times 2x is going to be 2x squared. X times -1 is -x. 3 times 2x is going to be 6x. And lastly, 3 times -1 is -3. Then the last step is going to be to combine like terms. So we get 2x squared, -x plus 6x is going to be 5x, and then -3. And again, I can graph this equation in Desmos, and when I do so, it should have x-intercepts at -3 and 1/2. Next, we want to work on factoring. So the first type of factoring is factoring a GCF, so greatest common factor. Typically, you only have 2 terms, and they have something in common that can be factored out. So in our first example, we have 9x squared plus 27x. So the first step is to figure out what that GCF is, what they have in common. So first I start with the numbers, something that goes into 9 and 27. And I want it to be the greatest common factor. So while 3 does go into 9 and 27, it's not the greatest. The greatest number is actually 9. Next, I look at the variables, x squared and x. So I look for the most amount they have in common, which in this case is only x. So now that I have the GCF, I'm going to go ahead and factor it out. So the GCF is always going to go in front, 9x. Now we divide our terms by the GCF to figure out what's left in the parentheses. So 9x squared divided by 9x is going to give us x, plus, and then 27x divided by 9x is going to give us 3. You always want to make sure that when you factor out a GCF, if you were to distribute that GCF back into the parentheses, you would end up with what you started with. So our second example, we have 64x squared plus 8x. So we're going to start off by identifying the GCF. So the greatest number that goes into 64 and 8 is 8. Next, we look at the variables, x squared and x, and they have an x in common. So just like with our previous example, our GCF, 8x, is going to be in front. 64x squared divided by 8x is going to give us 8x plus, and then 8x divided by 8x is 1. We have to make sure that because we started with 2 terms, there are still 2 terms left in our parentheses. And again, if I were to distribute that 8x back into the parentheses, I want to make sure I end up with what I started with. So next we want to look at factoring difference of squares. So difference of squares are the special case where we have a squared minus b squared, and it factors as a minus b times a plus b. So both of our terms are perfect squares and they're being subtracted. So our first example is 49x squared minus 144. So we have to figure out what number squared is 49x squared and what number squared is 144. So if I do 7x times 7x, we're going to get 49x squared. And if we do 12 times 12, we're going to get 144. Which means 49x squared minus 144 factors as 7x minus 12, 7x plus 12. We're going to do the same thing for 9x squared minus 100. So 3x times 3x is going to give us 9x squared, and 10 times 10 is going to give us 100, which means 9x squared minus 100 factors as 3x minus 10, 3x plus 10. It doesn't matter which parenthesis has the plus and which one has the minus. I could have easily written both of these with the plus first and the minus in the second parentheses. What does matter is that each set of parentheses, one of them is a plus and one of them is a minus. The last thing we're going to do with factoring is factor a quadratic with a coefficient of 1. So our first example, x squared plus 7x plus 12. When we're factoring, we want to figure out what numbers multiply to 12, but add to 7. If I start going through the multiples of 12, 1 times 12 is 12, but they add to 13. 2 times 6, which adds to 8. And then we end up with 3 times 4. So I have x plus 3, x plus 4. Next we have x squared plus 11x plus 10. So we're looking for numbers that multiply to 10, but add to 11. So if I start with the first multiple of 10, 1 times 10, those add to 11. So we're going to have x plus 10, x plus 1. Similar to the previous example, it didn't matter which set of parentheses came first. What matters is the signs in those parentheses. So I easily could have written these in their opposite way, x plus 4, x plus 3, and then x plus 1, x plus 10. The order that you put the numbers in the parentheses doesn't matter. All that matters is that the sign of those numbers is correct. The next thing we're going to do is identify the roots, also known as the x-intercepts of a quadratic from its graph. So if I'm looking at this graph and I want to identify the roots, I look for the x-intercepts. So in this case, the roots are at -2 and 1. Those are my x-intercepts. So it's pretty easy to identify the roots of a quadratic from its graph. You just look for the x-intercepts. So if you were given an equation, you would type it in Desmos and figure out based on the graph where the x-intercepts are. Okay. So next I'm going to start looking at functions. So on our first example, we're going to evaluate a function for our x value of -2. So when I evaluate a function, we plug in the x value we're given. So I have f of -2 equals 3 times -2 cubed minus 5 times -2 squared plus -2 minus 9. So when I go to evaluate this function, I can type the entire right side in a calculator and hit enter as long as I include parentheses. But I'm going to go step by step. So we're going to have 3 times, and now it's extremely important that when you are plugging a negative number in for x and raising it to an exponent, you put that number in parentheses. So -2 in parentheses cubed is -8, minus 5, and then -2 squared in parentheses is 4, and then plus -2 minus 9, I can go ahead and combine those, and I'm going to get -11. Because a plus -2 can change to a -2. So it's -2 minus 9, which becomes -11. So 3 times -8 is -24. -5 times 4 is -20. And then we still have our -11. So now when I do -24 minus 20 minus 11, we're going to end up with negative 55. So notice how that f of negative 2 is just the notation. I don't have to do anything with that left side when I'm evaluating a function for a value. Next, we're going to look at identifying the degree of the polynomials. So the degree is the greatest exponent. So you look for the term with the biggest exponent. It may not necessarily be the first term. It can occur at any point in your function. So my first function, f of x equals 2x to the 7th minus 5x to the 4th plus x cubed plus 3x minus 9. The term with the greatest exponent is to the 2x to the 7th. So the degree is that greatest exponent, which in this case is 7. On our second example, f of x equals 2x to the 4th minus 6x plus x to the 8th plus 3. The term with the greatest exponent is the x to the 8th term. So the degree in this case is 8. So next I'm going to identify the type of function represented by each graph. So these are our basic parent functions that we use if we're going to apply any transformation. So this first one, we have a line, which means we have a linear function. Our second graph is a V-shape, and the V-shaped graphs are our absolute value Next, we have our parabola, which is our U-shaped. Those are quadratic functions. And lastly, we have our kind of like our curved graphs. They grow towards one direction, and these are our exponential functions. So next I want to identify the number of real zeros. So real zeros, again, is just a number, a way to say number of x-intercepts. So what we're going to do is we're going to use Desmos. And I'm going to graph the equation f of x equals 3x to the 5th plus x to the 4th minus 4x cubed minus 6x plus 1. And I'm going to look for the number of times it touches or crosses the x-axis. And in this case, there are 3 real zeros. I don't need to know what the real zeros are. I just want to know the number it contains. And there are 3 x-intercepts in this case. Next, we're going to deal with operations with functions. So I'm given my functions f of x equals x squared plus 4 and g of x equals x minus 7. The first operation we want to do is addition, so f plus g of x. So we're adding our 2 equations together. So we have x squared plus 4 plus x minus 7. So now we just combine like terms. There's no like term for x squared, so it stays x squared. There's no like term for x, so it stays x. And then 4 plus negative 7 is going to give us negative 3. So that tells me f plus g of x is x squared plus x minus 3. Next, we want to look at subtraction. So when we apply subtraction, we're going to do x squared plus 4 and then minus in parentheses x minus 7. Because I'm subtracting the entire equation, not just the first term. So in this case, my first step is going to be to distribute the negative into the parentheses. So it becomes x squared plus 4 minus x plus 7. So x squared still doesn't have a like term, and then we still have minus x, and then 4 plus 7 is going to give us 11. So f minus g of x is going to equal x squared minus x plus 11. Next, we want to do multiplication. So we have f times g of x. So when we multiply two functions, we have to put them in parentheses. So we're doing x squared plus 4 times x minus 7. And then we want to distribute. So x squared times x is going to give us x cubed. X squared times negative 7 is going to give us minus 7x squared. 4 times x is going to give us 4x. And then 4 times negative 7 is going to give us negative 28. And none of these have a like term, which means f times g of x is going to equal x cubed minus 7x squared plus 4x minus 28. Lastly, we want to look at composition. Okay, and I'm going to find f of g of x and g of f of x. So remember, the order of composition does matter, and it's always the second equation that plugs into the first. So if I'm going to find f of g of x, that means I'm going to take my equation g and plug it in for the x in f. So f starts off with x squared, so I'm going to replace that with x minus 7, and then squared, and then we're going to have the plus 4. Now, I can't just distribute that squared into the parentheses. X minus 7 squared is x minus 7 times x minus 7. Then we still have the plus 4. When we distribute the x minus 7 to the x minus 7, we end up with x squared minus 7x minus 7x plus 49. And then we still have our plus 4. So combining like terms, we're going to get the f of g of x equals x squared minus 14x plus 53. Our second composition, g of f of x, we're going to take our function f and plug it in for the x and g. So g starts off with just x, so that's going to be x squared plus 4. And then we have minus 7. So now I just have to combine like terms, and we end up with x squared minus 3. Next, I'm going to use the vertical line test. So the vertical line test allows us to determine if a graph is a function. So how we use the vertical line test is if I draw vertical lines through the graph, and at any point, any vertical line touches the graph in more than one place, it's not a function. So in this case, every vertical line I have drawn intersects my circle in more than one place. So this is not a function. If we look at our second graph, if I draw vertical lines, they're only ever going to touch the graph in one place, which means that our second graph is a function. So next, I want to identify the transformations that have been applied to the function f of x equals x squared in order to obtain f of x equals negative 5x squared plus 10x plus 1. So what we're going to do here is we're going to use Desmos, and we're going to graph our original function, f of x equals x squared, and then we're going to graph our new function, f of x equals negative 5 x squared plus 10x plus 1. And we want to look at what we have to do to our original graph in order to get our new graph. So the first thing I've noticed is, if you're looking at Desmos, is that they open different directions. So that means there has been a reflection across the x-axis. I also noticed that the vertexes aren't in the same place, which means there's been some type of translation. So my original vertex is at 0, 0. My new vertex is at 1, 6, which means we have shifted right 1 unit and up 6 units. Okay. The last thing I notice is that my new graph is skinnier than the original. So that means it's been stretched by a factor, and in order to figure out what that factor is, you look at the number that's in front of the x squared. Not its sign, just the number. So in this case, the number in front of x squared is 5, which means it's been stretched by a factor of 5. So there have been 4 transformations that have been applied to f of x equals x squared in order to obtain our new function. Next thing we want to do is find the inverse of a given function. So we have the function f of x equals 4x minus 7. The first step in finding any inverse is to first write your equation is y equals. So we have y equals 4x minus 7. Next, we want to switch x and y. So we end up with x equals 4y minus 7. And lastly, we want to resolve for y. So that means adding 7 to both sides. So we get x plus 7 equals 4y. And then we want to divide both sides by 4. So that means my inverse function is x plus 7 all over 4. Next, I want to calculate slope. So in order to find the slope of the line between 2 points, we use the formula m equals y2 minus y1 over x2 minus x1. So when you label the points x1, y1, and x2, y2, it doesn't matter which point you choose as which. So I'm going to choose the point 4, 5 to be x1, y1, and the point -1, -7 to be x2, y2. So when I plug my values into my slope formula, we're going to get -7 minus 5 over -1 minus 4. So -7 minus 5 is going to give us -12 over -1 minus 4, which is -5. I can't simplify 12 over 5, but since I have a negative in the numerator and the denominator, those will cancel out to give me 12/5. Next, I want to look at some expressions. So first is evaluating an absolute value expression. So we have the expression -2x times the absolute value of 5y. And we want to evaluate it for x equals 4 and y equals -3. So first I'm going to plug in my value. So -2 times 4, and then in the absolute value, 5 times -3. -2 times 4 is going to be -8. Then in the absolute value, 5 times -3 is -15. Now, when I evaluate the absolute value of -15, so remember, absolute value is distance from 0. So -15 has a distance of 15 from 0. So we end up with -8 times 15. The -8 does not change signs because it is on the outside of the absolute value. Any number on the outside of the absolute value always keeps its sign. So now -8 times 15 is going to give me -120 as my final answer. Next, we want to simplify some expressions. So anytime we're simplifying an expression, we want to distribute any numbers into the parentheses and then combine like terms. So our first example, 4 times 3x minus 1 plus 2 times x minus 7 plus 5. If we distribute the 4 into our first set of parentheses, we get 12x minus 4. Then we distribute the 2, so plus 2x minus 14. Then we still have plus 5. So now I want to look at identifying like terms. So 12x and 2x are like terms. So that's going to give me 14x. And then negative 4, negative 14, and 5 are like terms. So when we do negative 4 minus 14 plus 5, we get minus 13. So our expression simplifies to 14x minus 13. Our second example, 3 times 7x plus 4 minus 9 times x minus 1 minus 5. We're going to distribute first, so 21x plus 12 minus 9x plus 9 minus 5. So that negative 9 is distributing to a negative 1, which is going to change it to a plus 9. So again, I'm going to combine like terms, 21x minus 9x. And 21 minus 9 is going to give us 12x. And then we have 12 plus 9 minus 5. And 12 plus 9 minus 5 is going to give us 16. So the last thing we have are simplifying expressions with exponents. So the biggest thing here is everything in parentheses gets raised to the exponent. So in our first example, we have 4x cubed times 7y squared. So everything gets raised to the exponent. So 4 cubed x cubed times 7 squared y squared. Now any number we can evaluate raised to an exponent. So 4 cubed is 64. So we have 64x cubed times 7 squared is 49. So 49y squared. Now, any numbers can be multiplied together. So when we do 64 times 49, we're going to get 3,136. And then x cubed y squared can't multiply together, so it's just going to stay x cubed y squared. We want to do the same thing for our last example. So 12k squared times 2t to the 5th. So we have 12 squared k squared times 2 to the 5th t to the 5th. 12 squared is 144. So 144k squared times, and then 2 to the 5th is 32 t to the 5th. Then again, we can multiply any numbers together. So we do 144 times 32, and we're going to get 4,608 k squared t to the 5th. So this covers everything that you are likely to see on your SLO. Please contact me if you have any specific questions. And again, you are allowed to use this on your SLO, and I highly recommend you do. Any formulas or sentences that I wrote on here to kind of help explain the process, I would definitely have written down as well, so that it's easier for you to remember what you did in order to get the answers in some cases. Also remember, you can use Desmos, so have that open. And if you don't have your own calculator, please have that Desmos scientific calculator open. That's on Classroom as well.